Welcome to Thermodynamics 1. This course is all about understanding how energy moves and transforms around us. Think about engines, refrigerators, and even your body. They all obey the same basic principles. In this first session, we'll start with the foundation: what thermodynamics really means, why it's so important, and how it applies to real life. By mastering these basic concepts, you'll have a solid base for everything else we'll cover. So let's get started on this journey by keeping things simple, clear, and practical.
1. Thermodynamics and energy. Let's talk about what thermodynamics really means. It's the science of energy, how it moves, transforms, and powers everything around us. Even the name tells us the story. Therm means heat, and dynamis means power. The most important idea is simple. Energy can't be made or destroyed, just converted. This is called the conservation of energy principle. The first law of thermodynamics explains this conservation in action, while the second law reminds us energy always loses quality. Things get less useful over time. You'll see these laws at work in engines, power plants, fridges, and even in your car's AC. Thermodynamics is everywhere energy is used, and understanding it helps us design better, more efficient systems.
2. Importance of dimensions and units. Let's talk about why units and dimensions are crucial. Every physical quantity, like mass, length, time, or temperature, needs a dimension to make sense. Without them, numbers are meaningless. We mostly use SI units, meters, kilograms, seconds, Kelvin, because they're standardized globally. But in some places, like the US, English units, like pounds, feet, and Fahrenheit, are common. The key rule here is dimensional homogeneity. Every term in an equation must have the same unit, or the math falls apart. And when we mix systems, we use unity conversion ratios, like 1 inch equals 25.4 millimeters, to stay consistent. Mastering units keeps your calculations accurate and your engineering solid.
3. Systems and control volumes. Let's break down how we study thermodynamics. First, we define a system. That's just the part of the world we want to focus on. Everything else is called the surroundings. The boundary is like a fence. It separates our system from everything outside. Now, depending on the fence rules, we have two types of systems. A closed system lets energy flow in or out, but mass stays inside, like a sealed pressure cooker. An open system, also called a control volume, allows both mass and energy to cross, like a boiler or an engine. Understanding these categories keeps your analysis clean and focused on what really matters.
4. Properties of a system. Let's simplify how we describe a system by looking at its properties. First, we have intensive properties like temperature or pressure. These don't care about how much stuff you have. Whether it's 1 liter or 1,000, the temperature is the same. Then we have extensive properties like total energy or volume. These grow as you have more mass. Double the mass, double the volume. Lastly, specific properties are just extensive properties divided by mass like specific volume. This way, we get a fair comparison no matter the size of the system. Understanding these helps you avoid mistakes in calculations and makes your thermodynamics reasoning clearer.
5. Density and specific gravity. Let's make sense of how we describe how heavy something is. Density is the simplest. It's just how much mass you have packed into a certain volume, like kilogram per cubic meter. Specific volume flips it around. It tells us how much space each kilogram of material takes up. Now, specific gravity is even simpler. It compares the density of a material to water. If it's greater than 1, it sinks. If it's less, it floats. And since it's a ratio, there's no unit. These 3 properties help you quickly understand and compare materials in any engineering system.
6. State and equilibrium. Let's talk about what defines the condition of a system. This is called its state. The state is simply described by measurable properties like temperature or pressure. Now, for equilibrium, we want everything balanced. Thermal equilibrium means no temperature differences. Mechanical equilibrium means no pressure differences. Phase equilibrium means no changes like ice melting or water boiling. And chemical equilibrium means the composition stays constant. Lastly, the state postulate tells us something powerful. If we know just two independent, intensive properties, we can figure out the entire state of a simple system. This makes solving thermodynamics problems much simpler.
7. Processes and cycles. Now let's look at how systems change. A process is just a journey from one equilibrium state to another, like heating water from cold to boiling. A quasi-equilibrium process moves slowly enough that the system stays almost balanced the whole way, making calculations easier. You'll also hear about special cases. Isothermal means constant temperature, isobaric means constant pressure, and isochoric means constant volume. Lastly, we have cycles, processes that come full circle, returning to the starting point. Engines and refrigerators work in cycles, which is why they can keep running again and again. Mastering these concepts is key to understanding real machines.
8. Temperature and the zeroth law. Let's unpack an idea that's easy to grasp but deeply significant: the zeroth law of thermodynamics. It says if object A is in thermal balance with B and B is in balance with C, then A and C must also be balanced. This is why thermometers work. They match the temperature of whatever they touch. We use temperature scales to measure it: Celsius and Kelvin in SI units, Fahrenheit and Rankine in English units. The conversion is simple. Just add 273.15 to go from Celsius to Kelvin, or 459.67 from Fahrenheit to Rankine. Understanding this law makes all temperature measurements possible.
9. Pressure. Let's explore the concept of pressure, one of the most important concepts in fluid and thermal systems. Pressure is just force spread over an area, measured in pascals or Newton per square meter. Absolute pressure starts from a perfect vacuum. It's the true pressure. Gauge pressure is more common in daily life, measuring how much above or below atmospheric pressure you are. If your absolute pressure drops below the atmosphere, we call it vacuum pressure. Lastly, pressure changes with depth following a simple rule. Deeper means higher pressure, thanks to the weight of fluid above. This equation, P equals PATM plus rho GH, shows exactly how depth influences pressure.
10. Pressure measurement devices. Let's discuss how we actually measure pressure. The barometer is your classic tool. It tells you the atmospheric pressure, like in weather forecasts. A manometer uses a simple fluid column to compare pressures, easy and reliable. The Borden tube is common in industry. It bends when pressure changes, moving a needle. And finally, pressure transducers are the modern option, turning pressure into electrical signals for digital systems. Whether it's weather stations or advanced engines, these devices are how we make pressure visual and measurable.
11. Problem-solving technique. Let's finish by learning how to approach problems like an engineer. Always start with a clear problem statement. Know exactly what you're solving. Then sketch a simple diagram so it's easier to visualize. Make smart assumptions to simplify. Apply the correct physical laws and find the right property values. When you calculate, use these values correctly. And finally, always verify, does the answer make sense? Tools like engineering software or equation solvers can help, but remember to respect significant digits. Don't pretend your answer is more accurate than your data. Follow these steps and you'll solve problems systematically and confidently.